One final example of being able to work through a surface area problem in 3 dimensions. Suppose we have a cylinder that's bounded in by a rectangle on the xy axis of 0, 0, 4, 0, 0, 2, and 4, 2. So first thing we're going to do, we're going to construct the region. So anytime you're given some coordinates, that's probably the best thing to do. So 0, 0 is just going to be our origin. 4, 0 is going to be to the right 4, 0, 2 up 2, and then 4, 2 is going to be that coordinate that's kind of like the linchpin of all of it. So we have 4 different equations. We have the equation x equals 0, we have x equal 4, we have y equal 2, and y equals 0. So those are our bounds. The good news is, because it's a rectangular region, we don't necessarily have to worry about any variables, which it means it could be either a type 1 or a type 2 region. But of course we want to wait to see what the integral tells us. We're going to solve for z, so we're going to subtract y squared, so z squared is going to be equal to 9 minus y squared. That means that z is going to be the root of 9 minus y squared. To be able to find the surface area, we have to find the partials of each of those. So f sub x, because the function has absolutely no x's in it, just goes to 0. Another way to write z, 9 minus y squared to the 1/2. So fy can be written as 1/2 9 minus y squared to the minus 1/2. So you subtract 1. We can't forget about the chain rule. So we have a negative 2y as a result of that interior derivative. Okay, so don't forget about your chain rule. If we want to rewrite that, another way to rewrite this, canceling out the 2 and the 1/2, is negative y over the square root of 9 minus y squared. So check your partials, make sure those are okay, check your setups. If we substitute back into the surface area formula, that's going to be the double integral of some value or some area a. That's going to range, or I'm sorry, each of the parallelograms is going to be the tangent vectors squared. So it's going to be 0 square or the cross product square. So 0 square plus negative y over root 9 minus y square, quantity square, plus 1 dA. Now this integrand is going to need a little bit of cleaning up before we can determine if it's a type 1 or type 2 region. If we clean up what's inside, double integral of a, negative y square is just y square, positive y square, square root of 9 minus y square, squared, 9 minus y square, and then finally we still have that plus 1 dA. Unfortunately, as it looks, it doesn't look like it's going to be an integral that we can evaluate very nicely. However, what we can do is we can turn the 1 into 9 minus y squared over 9 minus y squared by using a least common denominator. Right? So this is a technique you might remember from Calc 2, is being able to rewrite and try to get one term under the radical. So that's our double integral of a, square root of y square, 9 minus y square, plus 9 minus y square over 9 minus y square. So that's our 1 dA. And fortunately, we notice that we have a y square and a negative y square, so those are going to cancel. So 2 ways that we could write the double integral at this point. We could write it as a singular radical, so double integral of some volume a, square root of 9 over 9 minus y squared dA. Remembering the rule that the square root of a over b is equal to root a over root b, we could rewrite this as 3 over root 9 minus a squared. So double integral of 3 over root 9 minus y squared. We still have dA because we're not sure whether we should use a type 1 or a type 2 region. Alright, so we're this far, alright, and we've done some good work to be able to simplify it, okay, but unfortunately we're not completely done. Alright, so Last thing we're going to do at this point is we're going to decide whether it's a type 1 or a type 2 region. The good news is that the integrand is basic. It's actually the antiderivative of arcsine of y over a, where a is the square root of the constant. Take a look at your basic rules with that sheet of integrals that I provided, and what you'll see is that this is indeed one of the basic integrals. Alright, so let's go ahead and let's rewrite this as a type 1 region. Okay, so as a type 1 region, we're going to get integral. Now we're going to do x 0 to 4 first, then y 0 to 2, factoring the 3 out front, 1 over the square root of 9 minus y squared, and then we have dy dx. Right? Now we're going to see this becomes trivial. Now we're going to end up with, in 3 integrals, 0 to 4, this becomes arc sine of y over 3, and that's going to go from 0 to 2 dx. Okay. In fact, we could have just moved the dx inside of the integral as well to make it its own separate integral. All right. We're going to wind up with 3 integral from 0 to 4. I'm going to substitute 2 and I'm going to substitute 0. So we get arc sine of 2/3 minus arc sine of 0/3. Now we still have dx. Arc sine of 0/3 is arc sine of 0. Arc sine of 0 is 0. Alright, so we just wind up with an arc sine of 2/3. So a couple ways we can write this. Okay, we could write this as 3 arc sine of 2/3 integral from 0 to 4 of dx. And remember, because again, this is just a constant, and anytime that we have an upper bound of 4, a lower and a lower bound of 0, and then we have dx or dy or d theta or d rho, whatever it is, it just becomes that upper bound. So now we can write this as 3 arc sine of 2/3 times 4, or ultimately 12 arc sines of 2/3. And 12 arc sines of 2/3 does not have a precise value that we can simplify very nicely. It just stays 12 arc sines of 2/3.